Hello. I want to give you an intuitive sense of the art and science of Bayesian modeling. This primer draws from data for Max Scherzer, who pitches for my beloved baseball team, the Washington Nationals. In this primer, I want to introduce three key ideas about Bayesian modeling. First, modelers assume that the system that they are modeling conforms to probabilities. These probabilities can be estimated with mathematical models. Third, modelers use various techniques to evaluate their model's performance. Let's begin by asking, what are probabilities and where do they come from? To answer the second question first, probabilities are based on actual observations. For example, here is a bar graph of the number of pitches at various speeds that Max Scherzer threw in 2015. These observations can be translated into something called a probability distribution. Imagine that I wrote the speed of each individual pitch on a slip of paper and put these slips of paper into a hat. I pull out one slip of paper randomly and tell you, I will pay you $100 if you can correctly guess the speed written on it. What would you guess? If you wanted to maximize your chance of winning, you would guess the most probable outcome, which is about 87 miles per hour. Now look at the probability distribution for Stephen Strasburg, a teammate of Scherzer. Notice that Strasburg throws pitches in the 75 mile per hour range more frequently than Scherzer. Notice too that this pattern is generally consistent from year to year. When modelers assume that reality conforms to probability distributions, they assume that there are factors that influence the consistency of patterns appearing in the observations they collect. In this case, perhaps there are certain habits that Scherzer and Strasburg have picked up in a lifetime of pitching, and these habits result in the patterns in their probability distributions. If this is true, we can make use of these patterns to make predictions. But how? Here is another probability distribution. It shows the probability that Scherzer will throw a good pitch based on 2015 data. For our purposes, a good pitch is any pitch that does not result in a hit or a ball. This is called a Bernoulli distribution, used when there are only two possible outcomes. The distribution shows that Scherzer's pitches have a 60% probability of being good. Scherzer certainly does whatever he can to throw a good pitch, but chance also plays a role. A modeler assumes that a good pitch results from both random and non-random or causal factors. Based on this assumption, a modeler will try to mathematically predict the outcome of a pitch. In this example, the model assumes that a good pitch conforms to a Bernoulli distribution, which approximates the random aspect of a pitch's outcome. But the model also assumes that part of this distribution results from causal factors, such as ball speed and placement. How good is this model? One way to evaluate the model is through mathematical simulations. Using various ball speeds and locations, I ran this simple model almost 10,000 times and obtained these results. As we can see, the model overestimates the probability of a good pitch and comes up with a correct prediction only 60% of the time. Given the simplicity of the model, we should not be surprised that this model performed somewhat poorly. With more data and better algorithms, we can probably improve the model. But let's put off that task for another time. For now, play ball.
Strike out, baby!